Okay, so now I'm going to talk about some inverse hyperbolic functions. So the inverse hyperbolic sine function would be y equal sin to the negative 1x. Now that's not the reciprocal, this is like the inverse function. And so in that case, that would be, you could write that as hyperbolic sine of y equals x would be an equivalent equation. And here's the graph of the hyperbolic sine's inverse function. And then if you want the hyperbolic cosine of x, that would be equivalent to saying that the hyperbolic cosine of y equals x. So that function just looks like this. And then here's the hyperbolic, the inverse of the hyperbolic tangent function. And that would be equivalent to saying that the hyperbolic tangent of y equals x. And there's the graph of that. And then here are the graphs of the hyperbolic, the other inverses. Hyperbolic secant inverse, and that would be secant. That actually should say secant, not sine. So that should say hyperbolic secant of y equals x. And then here, y equals the hyperbolic cosecant's inverse. So that would be hyperbolic cosecant of y equals x. And then over here is the hyperbolic cotangent, the inverse of the hyperbolic cotangent, which would be equivalent to saying the hyperbolic cotangent of y equals x. So those are the inverse hyperbolic functions and their graphs. And there's actually a few identities. Now, let me just briefly tell you that if you wanted to find the inverse hyperbolic functions, you could actually write them in terms of the inverse of the e to the x forms that we discussed in the previous section. But if you did, they would actually involve logs, because generally when you have a function that involves e to the x, its inverse involves a log. So we won't worry about that for now. Okay, so now here are some identities. The inverse hyperbolic secant of x is actually equal to the inverse hyperbolic cosine of 1 over x. The inverse hyperbolic cosecant of x is equal to the inverse hyperbolic sine of 1 over x. And then the inverse hyperbolic cotangent of x is equal to the inverse hyperbolic tangent of 1 over x. Now, as far as the derivatives of these are actually given here. So here are the formulas for the derivative. So the derivative of the inverse hyperbolic sine function of u would be 1 over the square root of 1 plus u squared times du over dx. And then the inverse hyperbolic sine of u, the derivative of that would be 1 over the square root of u squared minus 1 times u prime. And in this case, some of these have conditions, like here u has to be greater than 1. For this one, the derivative of the inverse hyperbolic tangent of u would be 1 over u squared minus 1 times u prime. And then the derivative of the inverse hyperbolic cosecant of u would be minus 1 over the absolute value of u times the square root of 1 plus u squared times u prime. And of course in this one u cannot be 0. And the derivative of the inverse hyperbolic secant of u is equal to minus 1 over u times the square root of 1 minus u squared times u prime. And for this one, u must be between 0 and 1. And then finally for this one, the derivative of the inverse hyperbolic cotangent of u is 1 over 1 minus u squared times u prime. And for this one, the absolute value of u must be greater than 1. So we're not going to worry about those conditions that are listed below them, but let me go ahead and differentiate a couple for you. Okay, so if we have the hyperbolic sine of x cubed, then the x cubed must be the u, right? So the derivative of hyperbolic sine of u is 1 over the square root of 1 plus u squared. Okay, so we would have 1 over the square root of 1 plus x cubed squared. And when you square x cubed, you get x to the 6th. Now, don't forget the chain rule. You got to yank the chain. So then we have to multiply by the derivative of u. And since u is x cubed, the derivative of x cubed would be 3x squared. So we'll end up with 3x squared over the square root of 1 plus x to the 6th. Okay, we'll just do one more. To take the derivative of the inverse hyperbolic tangent of 5x, well, let's find that one. Here it is. So we would do 1 over u squared minus 1. So in our case, u is 5x. So we would have 1 over, and then we would square the 5x. So we would get 25x squared, and then minus 1. And then don't forget to multiply by u prime. Well, since u is 5x, we would multiply by the derivative 5x, which is 5. So I'd get 5 over 25x squared minus 1. Okay, now there are some integrals that we can look at here. So for instance here, if you integrate du over the square root of a squared plus u squared, it actually integrates to the inverse hyperbolic sine of u over a plus a constant. And then you can read the rest of them. Here, if you integrate du over the square root of u squared minus a squared, it integrates to inverse hyperbolic cosine of u over a plus a constant. And so let's look at some integrals. Okay, let me make this a little bit smaller so we can kind of see formulas that we're going to use here. Okay, so here I have x dx over the square root of 25 minus x to the 4th. Okay, well, I know that 25 is 5 squared, so that I could say that's a squared. And I know that if I square x squared, I get x to the 4th. So I could say that's u squared. So u could be x squared. So this is 5 squared times x squared squared. So a would be 5, and then u would be x squared. But I got to make sure I have the du. So let's see, if u is x squared, then du would have to be 2x dx. Okay, well I have x dx, so I need a 2x dx. Okay, that's no big deal, so I'll put a 2 here and a 1/2 on the outside. That way I have my 2x dx. So there's my du. Alright, now the bottom now is actually of the form a squared minus u squared. See, a squared minus u squared, where a is 5 and u is x squared. So I went ahead and wrote it like this so that we could actually look for the formula. So let's see if we can find a formula for that. A squared minus u squared. Okay, let's see, where do we have that? There it is. It's the second one here. So du over the square root of a squared minus u squared. Whoops, doesn't look like that's it, is it? Dang it. Okay, let's just start over on this problem. So just wipe the memory about what you just saw a minute ago. So, because I changed it. So the integral would be x dx over the square root of x to the 4th minus 25. Now, that's the same as x dx over the square root of x squared squared minus 5 squared. So if we let u be x squared and a be 5, then this is actually the square root of u squared minus a squared. Okay, and that's going to take us to this formula here. Now, but I got to make sure I have the du. So if u is x squared, then du would be 2x dx. So what I need to do is I need to multiply the x dx by 2 and then multiply the outside by 1/2. So now this is my du. And on the bottom I have the square root of u squared minus a squared. So basically I have this form in the integral. So now I go back to this formula. It integrates to the inverse hyperbolic cosine of u over a. So now, so I would have 1/2 because I had a half out here in order to get the du. And then it's going to be the inverse of the hyperbolic cosine of u over a, and then plus a constant. Now remember, u is x squared and a is 5, so let's plug those in. So we get 1/2 times the inverse hyperbolic cosine of x squared over 5 plus a constant. So there's your final answer. Now I do want to warn you that these hyperbolic inverses can be written as log functions. So if I have time, I'll show you some of that, but I don't know if I'll have time on this video. Okay, so the next one here, 2dx over 3 plus 4x squared. Okay, so I'm going to write that. I can write 3 as the square root of 3 squared, and I can write 4x squared as 2x quantity squared. So if you say a is square root of 3, u is 2x, then du would be 2dx. So I have the du here. Then this actually takes the form of du over the square root of a squared plus u squared. And so when you integrate du over the square root of a squared plus u squared, that would be the first formula here, and that would be the inverse hyperbolic sine of u over a. And then so I have the inverse hyperbolic sine, since u is 2x and a is square root of 3, of 2x over square root of 3. And I'm evaluating it from 0 to 1. So if I plug 1 in, I get the inverse hyperbolic sine of 2 over square root of 3, and then minus the inverse hyperbolic sine of 0. And actually the inverse hyperbolic sine of 0 is 0, and so the answer is the inverse hyperbolic sine of 2 over square root of 3. Okay, so you'd have to use a calculator or a computer to get that answer. Let me see if I can find those relationships for you and show you how these hyperbolic inverses are related to logs. Okay, I got these off of Wikipedia, so you might want to double check them, but just wanted to share with you that these arc or inverse hyperbolic functions, they do have another way that they can be written. And remember a while ago I mentioned that since the hyperbolic functions can be written as functions involving e to the x, then it makes sense that their inverses can be written using a natural logarithm, since the natural log of x is the inverse of e to the x. So also some of the formulas that are derived are actually derived by using the log form, and so that might be helpful for you to know. So let me just go ahead and show you that a couple of these. So the inverse hyperbolic sine function can also be written, I've seen it written both ways, as r sine h to the negative 1 or arc sine h to the negative 1. So those are other ways to write it. But its log form is the natural log of x plus the square root of x squared plus 1. And then the inverse hyperbolic cosine function, also r cosh or arc cosh with the inverse, can be written as natural log of x plus the square root of x squared minus 1. And then I've also given you the inverse hyperbolic tangent here. It's written as 1/2 natural log of 1 plus x over 1 minus x. And then the inverse hyperbolic cotangent is 1/2 natural log of 1 minus x over 1 plus x. And then for the inverse hyperbolic secant, natural log of 1 plus the square root of 1 minus x squared all over x. And then for the inverse of the hyperbolic cosecant, natural log of 1 over x plus the square root of 1 over x squared plus 1. And these might be able to be manipulated into different forms, but basically these are functions that you're probably more familiar with, because with the logs, than say than in this form. But again, these forms are interchangeable. You could interchange this function with this function and so on. So anyway, that pretty much finishes this chapter on all of the integration techniques. So I hope you enjoyed.